if we looking at this circuitry we just talked about, this is the simplest circuitry involved in your motor control, which includes a sensory neuron, which coming from your possibly your muscle spindles, and then you including the synapses with a motor neuron, and that is innervating your muscles directly. Okay, so this is everything is happening within this circuitry that including your spinal cord. So say the synapses in the middle of your spinal cord. It does not really involving any upper, higher order brain regions like the basal ganglia, cerebellum, or cortex. Okay, so this is what we have to learn before you come into my part of the lecture about the reflex arc. And what today we're going to do is to moving further a little bit, and we're going to looking at the different regions. So Dr. Jingunis probably mentioned about the central pattern generator, right? So that within your spinal cord. Dr. Radin, have we talked about the central pattern generator?
No. Nope.
Okay. Okay, that's caught me a little bit off guard because I thought you guys mentioned, probably learned about the spinal cord contribution in terms of local motion. So if you, this is just a very quick before we move on to the next level. So the spinal cord, if you decelerate a cat, this is an ancient experiment people did, and they removed all the cerebral cortex and the cerebellum, and only leaving the spinal cord intact and the rest of the body intact, and put the cat into the treadmill. And what then they start the treadmill, and so they see this cat start walking. Okay, so basically that is suggesting the very basic neural circuitry that involved in the walking and galloping, trotting, all involved localized in the spinal cord. So we call this neural circuitry central pattern generator. Okay, so that is something we don't need to even have the cortex input or basal ganglion input that we're able to generating these very basic patterns of movement. And so that is spinal cord actually involved in that. So today we're going to moving upward a little bit and see how the other brain regions are doing. And first, let's take a look at the more of the people call the ancient brain. Okay, so this is including several regions, so we can see from this diagram. First of all is your cerebral. Okay, so this is the very large regions, actually contains about 50% of the neurons in the central nervous system. And that's going to have a heavy input in your movement. There's also several structures we listed here, including red nucleus, superior colliculi, vestibular nucleus, and reticular formation. All these regions are located in the brainstem. Okay, so they are sending input. So the neurons originated in these regions, and the synapses with the motor neurons in the lower the spinal cord region, and then changing the motor output. They could be increasing or decreasing the neuron sensitivity, and so that's creating the control to the motor nucleus and motor neuron. All right, so if we take a look at these regions, they have a very their function pretty much is for posture control and equilibrium. There are several structures that you probably are familiar with, and so superior colliculi. Okay, what is that? When we talk about it, we talk about it when we talk about the visual reflex, and then later on we talk about it during the vision processing. Okay, so that is important when you control your head movement and eye movement. And the vestibular nucleus and the reticular formation, as we're showing the other two here, this is important for the posture control, especially equilibrium. So vestibular nucleus is the second order neurons that the synapses with the vestibular fibers. So those are the nerves coming a part of your cranial nerve 8. Okay, so those are very important for the equilibrium and the posture control. Okay, so you may noticing that we talked about 4 tracts here, right? Vestibular spinal, reticular spinal, tectal spinal, and rubospinal. So these names is a very typical anatomy names, with the very first half is indicating the starting point. So vestibular means the starting point is vestibular nuclear. Reticular means the starting point is a reticular formation, which is the structure we talked about, the cross out in your brainstem region. And the tectal spinal, okay, tectal means the 4 structures. You remember in the midbrain we have a superior colliculi and inferior colliculi. So together they are forming those 4 nuclear type structures. So this is a tectal. And that giving the neurons originated in that pathways are coming from the superior colliculi. And the rubal means red, so it's a red nucleus. We mentioned that a little bit when we talk in the central nervous system. So this is the initial part of all the nucleus that was originated, the pathway was originated from. And the later part of the spinal all means the termination part. So they all terminated in some level in the spinal cord. Okay, so we have learned these 4 pathways now, and they call the brainstem pathway because they originated from the brainstem, and sometimes we call them indirect pathway because they are not directly controlled by your upper brain. Okay, so one thing before we move on is many animals, without the cortex, the cerebral cortex input, they are able to achieve very complicated skilled movement just by involving of these structures. I'll give you one example. And so for the frogs, they want to catch a fly. And this is actually very complicated movement. They have to see the fly, they have to turn their head, they have to stick the tongue out, and have to shoot right towards the fly and then going back. And all this involvement does not really require any cerebral cortex control. So everything is actually done by this at this level we have talked about. So for humans, we have a significant amount of these tracts actually originated from your cerebral cortex. So this is a tract that we call cortical spinal pathway. Okay, sometimes we call it pyramidal tract. The different resources will tell you probably why we name them pyramidal tract. Some of them will tell you it's because of they originated from the pyramid, those pyramidal cells. Okay, so the other one is because they are across the midline in the brainstem region or area called the pyramids. So that's also part of the reason why they call it pyramidal tract. Anyway, so these tracts that originated from the primary motor cortex, they actually divided up into 2 tracts. We have these called lateral cortical spinal tract, which is located and transmitted in the very lateral part of your spinal cord. We have also the anterior cortical spinal tract, which is more of the anterior part of your spinal cord. So they're kind of separated. And 90% of those tracts actually cross the midline and innervated the other half of your body. Okay, so that's why the left side of the brain is controlling the right side of the body, and because they're crossing, 90% of them cross the midline in the brainstem region. We call it medulla region. We call it pyramids, just like we have said before. But also 10% of them do not cross the midline. Those tracts are very important for your posture and to maintain your posture. Okay. So there's another thing I want to mention here. Okay, so the lateral and the anterior, the differences between these 2 tracts, we're going to talk in a second. But generally speaking, the lateral is involved in the skilled movement in the limb. And the anterior part is involved in innervating the skeletal muscles of your axial, okay, more the middle part of it. The other pathway we have seen here is called cortical bulba, and we mentioned that before. Bulba means brainstem, so the end of the terminant part of the pathway is actually located in the brainstem region. So which means these pathways actually synapses with many of the nucleus of your cranial nerves. So like the trigeminal nerves, and you have the hypoglossals, they have several different neurons that nucleus that synapses, they're eventually innervating your eye muscles. So those are giving rise to synapses with those nucleus. So they are voluntary control of the muscle of the head and the neck. So if you group these pathways and based on their locations, this can give you some very useful functional information. So as we talked about before, lateral corticospinal pathway originated from your cortex, and the rubospinal tract that originated from your red nucleus. Okay, so in the midbrain. So these two actually is making the dorsolateral pathway. So both of these pathways involved in controlling of your limb and the very peripheral side of your body. Okay. So the others in the middle part, we can see there's a cluster of 4 of them. You have the anterior corticospinal, which originated from your cortex. You have the reticular spinal, which originated from the reticular formation, vestibular, nucleus, tactile, superior colliculi, and all of these 4 is controlling all of the torso, and this is giving rise to, together they call the ventral median pathway. Okay. So ventral median pathway, this is we basically mentioned all the tracks and the and their function already, and we know there's controlling the axial and the proximal muscles involving in postural control and equilibrium. And for the dorsolateral pathway, and we say this is a control for fine movement of your distal limbs, including your fingers. Okay, so here I have one thing that just trying to remind you of when we talk about red nucleus. We said red nucleus in human, at least in intact system, they do not have a very big function. Do you guys remember that? So that's why we say the red nucleus do not have a prominent function in humans. And generally speaking, they do excite the flexor motor neurons and inhibiting the extensor motor neurons. Okay, so I'm going to give you an example. And this is the posture of a patient who has a deceleration, like if you have a damage around the red nucleus level. Okay, so if you damage above red nucleus, the red nucleus is intact. What is the posture is going to give you is the lower one here. Okay, so these subjects were having, you can see their arms are flexed. This is when we have a deceleration rigidity, and when they're basically just showing this enhanced flexion action. And for example, if you the damage is below the red nucleus, so red nucleus do not have any influence. It's just if this is in the pontine region, and the subjects will look like that. So the flexion you see before was completely missing. So this can give the clinician some ideas about where the damage is. So those are indicating what the red nucleus do, especially in those pathological conditions. All right, so here I want to give you some of the some background on this experiment and ask you to answer a question. So this experiment was two monkeys, two sets of monkeys. So the first monkey was intact, and we call it control. And these monkeys, we asked them to pick up the food from a well. The monkey was able to pick it using their index finger and the thumb, and grab it and take it out. Okay, so then later on we damaged one set of these tract and asked the monkey to do the experiment again. So this is the one set of tract is actually descending tract. One of them we have talked before. And the monkey, you can see that when they're trying to grab it, they cannot grab the food anymore. Instead that they're doing is they're going to kind of scooping and sliding their hand over the food and trying to get the food out. So my question for you is, which tract do you think most likely damaged in this case? We have a minute for this one. Okay, let's take a look. Okay, very good. So most of you choose the corticospinal tract. Let me ask you, if I put a rubospinal tract in here, would you change your answer or not? Which one is more likely to be the one got damaged? We talked about the rubospinal being kind of irrelevant in most of the intact animals and was doing most with the flexor muscles. So if I put a rubospinal and the correct answer is still corticospinal, okay? And this is actually the experiments we did before, and basically these experiments indicating that damage to the corticospinal tract affects fine, distal, goal-oriented, and exploratory movement. Okay, so that's another kind of a summary for the corticospinal tract. All right, so before we move in towards the cortex, I want to spend a little bit of time talking about a very important region in your brain that it helps you to control your movement. This region is basal ganglia, and sometimes we call it the basal nucleus. The very early on, the kind of a finding about how important this region is through a bunch of disease. Okay, so we learn a lot about the basal ganglia through Parkinson's disease, through Huntington's disease, and so these diseases oftentimes have some common features. So these common features has a lot to do with the slowness of the movement in one hand. So we have this bradykinesia, which means the slowness of the movement, or akinesia, which means the slowness in delayed in initiating a movement, or having a very delayed or damaged spontaneous response. Okay, so that means akinesia, and Brady means slow, so A means no. So basically that tells you some of the deficit in the movement. We also see that this type of disease also involved with some change of the muscle tone. So cogwheel rigidity. This is sometimes if you want to, for example, if two people have the wrestling of your arms, okay? So normally this is when you're doing this movement, it's a continuated movement, right? When I apply, this is probably better to have doing it with another subject. So when I was trying to, my arm, my left arm is trying to do this flexion. Normal people, like all of us probably, this flexion is oftentimes very continuated. But during this condition, basal ganglia damage, these oftentimes has this kind of a jerkish looking movement like this. So the movement becomes very discontinuated and oftentimes very jerky, and so this we call the cogwheel rigidity. There's often these conditions involved with abnormal involuntary movement, like a tremor, apoptosis. Apoptosis is a kind of it's a very slow movement, extracting any movement. The balism is a very violent movement, and a dystonia. So all of these are indicating that your basal ganglia somehow seems to be increased or decreased activity that involved in the control of your cortex movement. We have a lot of findings since then did in the basal ganglia will support these evidence, support these conclusion, which means which is the basal ganglia enhances or decreases the activity through the motor cortex. Okay, so let's take another look at this schematic diagram showing you where the basal nucleus is located, and we're going to talk more about it. So basically, this diagram is actually very, very simplified, and I don't want you to misled by this diagram. But anyway, the basal nucleus here seems to get input from your sensory motor cortex, and it seems to be influence the sensory motor cortex through thalamus. Okay, so this is a very basic idea this diagram trying to get. And we're going to correct this image a little bit later. Okay, so I mentioned that people did a lot of research on the basal ganglia, and the people find that when you actually recording from the basal ganglia, you find that the neurons in basal ganglia start firing way before you actually start moving before the movement is started. So, which means this basal ganglia is important in the planning stages of the movement. And we also find that they are receiving input from the entire cerebral cortex. Okay, so this is also evidence suggesting that the initiating of the movement is one of the important functions for the basal ganglia. The other things that we get from those disease level is when you have a basal nucleus damaged, you see that you have a lot of unwanted movement. So suggesting that the basal ganglia, one of the other function is prevention of the unwanted movement. Okay. So I mentioned that we were going to give you a more precise role of the basal ganglia, which is the diagram showing here. And one thing I do not want you to be intimidated by this diagram. And I don't think that I'm requiring to remember all the connections and between every sub areas in the basal ganglia. But in order to really understand how this network is functioning, helping you to achieve movements, and it is necessary to have a close look at this diagram. Okay, so let's first take a look at what is the basal ganglia is involved. I told you before, I said your textbook, I followed McKinney when I introduced the basal ganglia. And I said this is not entirely true for many other textbooks and for many other researchers' papers. And this is one example I'm showing you. So here you have several regions important, the caudate nucleus and the putamen. And together, people call them striatum, okay? And you have also globus pallidus. This is structure your book mentioned that before. And if you separate it into more detail, they have external segments and internal segments. Okay. And the other regions that your book did not mention, McKinney book did not mention, is this subthalamic nucleus, okay, and also the substantia nigra, okay. So substantia nigra has two parts, SNPR and SNPC. Both are substantia nigra, just a subdivision. And okay, so we have, so basically we have to talk about these several regions. And now let's take a look at what is the input to your basal ganglia. What is basically the entrance for all the information for the basal ganglia? The entrance is your striatum. So all the inputs you're going to send is sending to the striatum. And so what kind of information you are sending? You're receiving information from the cerebral cortex, all the somatosensory, sensory motor cortex. So this is what we're showing here. And also you're receiving input from the thalamus. This is why I say the previous picture is not entirely accurate, because we also have the thalamus going to input to the striatum. Okay, what is the output of the basal ganglia? The output of the basal ganglia is actually two parts. One part is your globus pallidus, especially the internal segments. So what is this output sending to? They're sending inhibition to thalamus and to your brainstem. So here, what is the PPN? PPN stands for peduncle puncting nucleus. You don't need to know the name, but what is it basically sending is sending to the spinal cord, and then that goes to the brainstem, then goes to the spinal cord. Okay, so the other output here is your substantia nigra. Substantia nigra is one of the things we mentioned about very important in dopamine, in the Parkinson's disease, okay? So this is also sending inhibition to your thalamus. So what eventually thalamus do is the thalamus going back and to feed back to your cortex. So you can see that what is your basal ganglia actually doing is to sending negative feedbacks and changing and correcting planning of all this movement. All right, so we know what is the input, what is the output. And I told you, don't worry too much about the interconnections. And one thing I want to help you, for those who are interested in studying more about this diagram, this is a very classic diagram, and the reason I mention it about this diagram, even though it's so complicated, is it's going to be very helpful in the future when you're going to the biology of the brain and other courses talking anytime about the basal ganglia. This is the diagram, okay? So you see that there's a dotted line and a solid line here. The solid line means excitation, and the dotted line means, dashed line means inhibition. I'm going to give you two examples about how these diagrams help explain the conditions that we see, like Parkinson's and Huntington disease, okay? So first of all, if we're talking about the Parkinson's disease, every time we're talking Parkinson, we have to basically looking at the substantia nigra. We say it's because of these particular regions has a deficit, the dopaminergic neurons are damaged or this losing. So dopamine in here has sending two tracks, and they have the excitation tracks as we've seen here through the D1 receptors. And they also have the inhibition tract through here, through the D2 receptors. And so this information actually going to be, then later on relayed. For example, D1's information going to relay through this pathway, through this. Sorry, I'll try to give you a better color-coded. Okay. So what we see here, actually, okay, let's just look at the D1. If you remove this excitation to the striatum and reduce the striatum activity, we're causing less inhibition to the globus pallidus, the internal the segments. So of this less inhibition, we're causing excitation of your globus pallidus internal segments. This excitation due to this D1, the reduced D1 activity, will causing reduced activity in the thalamus. Okay, because this is stronger, you have a globus pallidus activity. This inhibition will causing decrease the level of thalamus information, and that will feed back to the cerebral cortex and have a decreased level of activity. That's why we see there's a kinesia and there's a bradykinesia. Okay, slowness of the movement. Yes, Jake. Yes. Yeah, that's exactly right. So through that D1 receptor. Okay. So I don't want to bore your brain out about the D2 receptor pathway, but I can just quickly tell you is the D2 receptor pathway actually going here. Okay, so for only those who are interested. So what is it going to do? It's actually, if you do the math after you got home, you can see that actually this is also going to decrease your activities in your brainstem region and in your thalamus that feed back to your in your cerebral cortex. So that both, I know this is complicated, but basically both of these pathways were reducing your activity, that the modal input to your muscles, that is contributing to your akinesia and bradykinesia. And there's also going to be a imbalanced input to the globus pallidus because of these different these different input, unbalanced, and that contributing to this rigidity, and this including to the unwanted movement, sometimes tremors. Okay, so the other thing I want to use this diagram to help you understand a little bit is the is the Huntington disease. What is the Huntington disease actually? The deficit in is this GABAergic input. You actually reduce the GABAergic input to your globus pallidus external segment, and what you can imagine to see here is if this inhibition is less, this activity, the globus pallidus activity is going to go up, and this inhibition is become stronger. So this is subthalamic nucleus activity is going down, and the globus pallidus internal, this segment is going to activity go down, and you have less inhibition to this PPN and thalamus. You're going to have increased activity. So that explains to you this involuntary movement, as we're going to see in a second. Okay. So as you can see, because of it's inputting both to the brainstem and to the cortex, and that's why we say it's regulating both dorsolateral pathway and the ventral median pathway. Okay. All right, so if we have any little bit appreciation of that little diagram we have just trying to explain. I know this is very hard to explain considering the amount of complexity there and the short of time we have. But you can see that the destruction of this nigra striata pathway, basically that's a substantia nigra to striatum, so that's called a nigra striata pathway. And that due to the loss of the dopaminergic neurons, and you see these patients will have all these symptoms we listed here. And I'm going to show you this movie so you can, investigate it yourself. So you see the tremor, the hand starts moving even during the resting condition. And the movement, it was asking to walk forward, and it was very slow. And they're going to show you the cogwheel rigidity. So for the normal people, there's a very continuated movement. And for this patient, let's take a look. So there's several levels, seems to got stuck. And those are called the cogwheel rigidity. And you see the movement, the way he grabbing the hand is very fast, but this is the fastest this gentleman can go. So you can look at the face, it's always kind of called a Parkinsonia mask, so there's no facial expression. This is showing the tremor, resting tremor. We sometimes call it pill rolling, because it's like rolling the pills. So the slow movement and the tremor on the hand. but the decrease of neural activity is pretty obvious in this patient. The fascinating gait, probably I didn't explain before, was the one when he was trying to make a movement. It was slow in starting of the movement. All right, so this is our Parkinson's disease. And let's take a look at a quick Huntington disease. This is, if I can fast forward a little bit. So Huntington disease is really slow. I'm just going to stop it here. Let me pretend that, I have the Huntington disease. So people in the Huntington disease oftentimes call it a Huntington dance. So this is actually having a lot of, the raving and those kind of flailing the movement of the arms and I want to fast forward these segments, but you can see that the gentleman, 38 years old, but it has that kind of a gait and a posture and a movement that is very characteristics of abnormal involuntary movement, as we underscored here. So this is probably not a very severe case, but when you have a very severe case, the arm started to to move really crazy. But you can imagine that with the neural pathway, the GABAergic block, GABAergic deficit we have described before. Okay, I'm going to stop here. This is very devastating, and this disease has a genetic basis and running within the families. So there's a 50-50 chances with any family who has this type of disease, and their offspring will get affected. And it also the quality of life isn't don't mention about that, but the people later on started to have a problem with talking, and then they will shortly after that they will actually die. So it's a devastating disease. Unfortunately, there's still no treatment for it. So only to kind of decrease the level of unwanted movement through drugs, but the treatment for the disease itself is very limited. Okay, so I'm going to go to a little bit more fun part of this lecture in my mind, and to talk about the motor regions in your cerebral cortex. So we mentioned that our human brain really is very tuned to and developed to conduct those very skilled movements. And our bigger brain, especially the cerebral cortex, not only able to allow us to produce a more skilled movement, but also be more flexible in conducting this movement and considering different contexts, different goals. So this is really very special about our human. So listed here are several regions that are important for the cerebral, important for the motor control. So first is the primary motor cortex, as we talked about before, is the precentral gyrus. And this is directly the originated place for your direct pathway, the pyramidal pathway, and so labeled yellow here. Right in front of this primary cortex is our secondary motor cortex. We sometimes call this area 6. Area 6 has two parts. The lateral part, we call it a premotor cortex, and the median part, we call them supplemental motor areas. And if you're looking at the more of these other regions in your brain, including a large area in the prefrontal cortex and the parietal cortex, you were talking about those association motor cortex. And so we're going to talk about each individual ones and see how much damage to it will causing any modal changes, modal function changes. Okay, so going from the very bottom of the whole entire central nervous system, and for now I'm skipping the basal ganglia. but you already should appreciating what the basal ganglia do for our body. All right, so the spinal cord, if we have any sever to the spinal cord, you know that we're going to lose the ability to sensing of that areas of the body, and we're going to lose the control of the motor control to that regions. And those are called, for our motor purposes, this is called a kind of a plagia, okay, plagic. So if this is savage only happening only to the lower part of your body, and we call it paraplegic. And if it is happening to the, if this is damages high enough and damage the influence the whole forelimbs, we call this quadriplegic. Okay, moving up a little bit for the motor cortex. Oftentimes the damage to the motor cortex is due to stroke or tumor, and oftentimes it's only affecting one of our brain. Okay, so that's why we have called a hemi, one side, either hemiplegia or hemiparesis. The differences between these two actually is the level of the serious. So if you have a hemiplegia, that means you're losing total control of your motor control of the one side of your body. And if you have a hemiparesis, that means it's a mild form of the one we just talked about. So the muscle control is there, it's just weak. So it's a weaker control, impaired control of the contralateral side of your body. Okay, so here I want to draw attention to is what will happen if you damage your secondary association motor areas. And this is a condition we call apraxia. Okay, so what is apraxia? The definition for apraxia is probably easier to do with exclusion than inclusion. So I'm going to give you an example what I mean by that. So the apraxia is basically this kind of disease is a loss of ability of generating coordinate actions, not due to loss of muscle control. Okay, so nothing wrong with the muscle control. It's just the comprehension of the movement and to execute those very coordinated actions without a compromise. But the muscle itself is still function. Okay, so that's called, that's when you know there's actually damage to the secondary and association motor areas, not the other rest of these motor control areas. Okay, so let me give you an example. This woman, if you tell her to move your fingers, she can move it, no problem. So the hands movement, the muscles, and this is all intact. But if you ask him to show me how you would open a door with a key, she seems to be lost. So the ability that she was holding a key and push it through into the door, and then turn it and open the door, and those functions are lost. So this is one example of what we call apraxia. Another example I can give to you is, so if you show this woman, okay, what is this? She will tell you it's a scissor, and her hand is still moving, you can control it. But if you ask her to show me how you're using a scissor to cut a paper, and then she seems to be lost. Similar things as if you ask her to do anything fancy with the cup. Okay, so this is oftentimes due to the stroke to the premotor or parietal cortex, which is involved in our secondary association motor areas. And usually this is oftentimes very severe when your damage is to the left side of the brain. So this is very, very interesting because it's very similar to when we talk about the Broca's areas, the Wernicke's area, talking about the fascia, right? So let's take a look. It seems like the left hemisphere plays more of a dominant role in terms of this tool using and the sequential movement. So in order to suggesting that, I'm going to actually ask you to do experiments in class with me. Okay, so I will have you to get your dominant hand out. Okay, so and then I will ask you to is touching your thumb with your index finger as rapidly as you can. Okay, I'll give you 10 seconds. And ready, set, go. Okay, stop. All right. now changing to your non-dominant hand. And do the same thing. Ready, set, go. Okay, now stop. All right, so remember what the result is, and remember which hand is faster, okay, for right now. And let's do another experiment. This time, I will ask you to sequentially touch each finger to your thumb. So first with your index, then the middle, and then the ring, and then the pinky. So over and over again. So touch it from what I just said and over again. And so first the dominant hand. Oh, okay, dominant hand. 10 seconds. Ready, set, go. Stop. Non-dominant hand. Okay, ready? Go. Stop. All right. So you all know based on your data what it looks like. What I'm going to ask you is discuss with the results showing on the blackboard on the projector, and I'll give you 1 minute, and then you have to tell me what these data suggest, and then you can relate to your own data. If you need any explanation, let me know. So basically, these diagrams are showing you exactly the experiment we did before. Trying to find the patterns of those diagrams. All right, ready? Okay, tell me what you think. All your neighbors, what your neighbor think? Okay, got it to move faster. So, yes?
It looks like the only difference is when you're left-handed and you're tapping your index finger to your thumb, like that seems to be a lot higher, but if you're left-handed and you're tapping sequentially, so slower than if you're right-handed.
Did everybody hear her? So it seems like the repetitive tapping, it is showing some hand dominance. So if you're a left-handed person and you're using left hand, it seems to be tapping faster than your non-dominant hand, right? This is true for both the lefty and righty. Yeah, okay.
Looks like the right-handers might be more ambidextrous, because it seems like that's the difference between the left and right hand.
Okay, yeah, that seems to be, see the huge differences in the lefties, but not so much in the right-handed, in the repetitive tapping. Okay. And what is the other diagram that's showing you? So she also mentioned before, is it seems like for both left-handers and right-handers, both when you're using the right hand to do the sequential movement, that is faster. And it seems the right-handed person are doing that faster than the left-handed person. Seems to be. Is that similar to the results you find? Okay. So this is actually interesting because of normally you would think the left-handed person, when they're doing any movement, will be faster in using their left hand. However, it's showing here is your left-handed person, when you're doing these sequential movements, still the right hand is still to be more efficient. And your right hand is controlled by your left hemisphere. So that's suggesting to us is your left hemisphere seems to be having some dominant role in doing these kind of sequential movements. Okay, so this is actually a study doing in fMRI to a bunch of left-handed persons, and when they were asking you to using the right hand, this is what is showing in the diagram. So left one is the right hand movement. what they see is you have an increased activity on the left side of the brain. That's typical. Because you want to control the right hand, your left hand side, of course, needs to be light up. And when you're asking them to do the right-handed movement, yes, the right side is light up too. But there's a significantly amount of activation happening in here, still in the left hemisphere. Okay, so this is really interesting. And you may be wondering, okay, if I ask some left-handed person to do the same experiment, would the result change? The results are actually very similar. So the left-handers show some similar patterns of this increased activity, even when you're using your increased activity in your left hemisphere, or even when you're using your left hand doing those sequential movements. So this is underscored that the asymmetric in ipsilateral activation is associated with the hemispheric spatialization rather than your hand dominance. Okay. So it seems like the left hemisphere has something unique about this sequential movement, and they actually people have many of the research findings showing that it's not just to the sequential movement, but also tool use. So this is the example we're showing using another fMRI study, having people to just think about they are going to use a tool. Okay, so if they're using a tool on your right hand, this is how the activity looks like. So left hemisphere is activated much more than the left hemisphere. This is straightforward. But when they're asking them to think about using tools using their left hand, still I will argue there's more activities in the left hemisphere than the right hemisphere. Okay. So this is showing our left hemisphere, their relationship with the praxis. Praxis is the word here. My definition is a skilled kind of sequential movement. Okay. So let's take a look at the people, how they are functional, represent the functional organization of the modal pathways. So there are many ways that you can describe these functional organizations. I'm going to talk about the two ways. One is called the mode of control. The other one is called a hierarchical organization. So mode of control basically is whether the cue or the driving force is external or internal. Okay, so external means, okay, I see, just imagine I have a donut right in front of me. I want to go grab it, and I see it at one, and so this is a very driven force with external kind of cues, and I need to adjust my behavior based on the location of this donut, and I have to go grab it. And, all this will be involved with external sensory guided. And what is internal? Okay, internal means when you don't need a lot of this sensory guided information. And for example, you close your eyes, can you still sign your name? You can still write your name. That's probably no problem. And those are open. Those are called open loop. And because there's no feedback, it's just the internal kind of driving force. So here, this diagram actually showing you the areas involved in those external mode and the internal versus the internal mode. So anything about this black dot, black arrows are showing you the external loop. So you can see that parietal cortex is very important in here, and the information is going into the premodal cortex, okay, and then this is be projected to the modal cortex and sending information down. And I'm not going to mention in both of the cerebellum and the basal ganglia because both of the structures are involved in both of these modal controls. And the internal ones is more of initiated from your prefrontal cortex. And so this is a sending projection to your supplemental modal areas. And from there, it goes to projected through basal ganglia or the premodal cortex that go into the modal cortex, the primary modal cortex. Okay, so the difference is really whether you're involving your parietal cortex or you're involving your prefrontal cortex. So in these two different two modes. And I'm trying to isolate these two. Oftentimes they cannot be really completely isolated. The other way people characterize the functional organization is through this hierarchical organization. So hierarchical organizations, as we can see, is first you have the parietal lobes involved using this special information like the donuts I was just described to you, and be able to generating a goal, and that I'm going to move my body and arms, extend my arms to grab that donut. And then you have these premodal and supplemental modal areas. It's going to translate the goal into a movement trajectory or action sequences. And this, of course, has to be involved in the basal ganglia, as we described before. But this is an action plan. How I'm going to get to the donuts? I have to cross these, monitors here. So I have to. The trajectory is this. If without the monitor, I may be able to just go grab like a straightforward. Okay. So of course, they're also going to be involving in the primary motor cortex, which is to translate the movement plan into actually move command that was sending through the motor unit to the activating the spinal cord. Okay, so that I have to make sure I don't trip over, I don't embarrass myself in front of you guys, and to be able to reach that donut. Okay, so those are involved in this maintaining the reflexes and maintain the stability, activating the muscle. So this different hierarchical organization of your motor control. Okay, so we just mentioned about the different areas we're involving in the brain, and it's a kind of a very rough, very big picture about the areas involved in it. And the next 10 minutes also, I'm going to shift my gears and to kind of peek under the hood to see how this single cells model in the motor cortex, in other regions that involved in motor areas, how they function in order to contributing to this movement. Okay, so this is in my mind, oftentimes the most challenging part of this lecture. Okay, so the question, the overarching question I'm asking right now is what information is coded by single cell in motor regions of the cortex? Okay, so to understand that, we use animals, monkeys, to do that. And this is an experiment I'm going to show you. The experiment is basically as a monkey just sitting in front of a table, and this table has 8 different lights and could potentially lit up, and there's a handle in the middle. So the monkey is trained whenever there's a light to illuminate it, and the monkey has to push the handles towards that direction. So they could potentially go into the, to going up, going to the left, going down, and to 45 degrees. And so there's 8 different areas that the monkey can go. Okay. So what we have, what we do into the monkey is we actually drop the electrodes into any areas that we're interested in the motor areas, in the cortex. And then we start to recording that single neuron activity. Okay, this is the recording is actually showing in the right side of this figure, and we have it here. So what I want to draw your attention is to let's take a look what this diagram is telling us. Okay, so what we're showing here is 8 different directions. So let's take a look at the top of the directions, and when the movement is going towards upward, which is 90 degrees, and the color coded region here means the movement actually happening. Okay. And there's a dotted line, so there's lines going, 5 lines here. These 5 lines, each line is indicating more movement. So basically, the monkey did it 5 times. So that's a 5 of the lines here showing you 5 trials. So each line, they have these black dots. Each black dot representing a neuron firing action potential. So what we can see here is there's, before the action was actually happening, and the blue region I'm labeling here, there's a kind of a tonic activity happening, and then when you have a movement actually happening, you may or may not changing the firing behavior. And after your movement is finishing, and they're returning back to your original firing behavior. Okay? So is that clear? So let's take a look at when the monkey was pushing the ball to the 180 degrees here. What do you see here? Can you tell me if the neurons actually firing more or less during these 5 tries when they're moving towards left? Can anybody tell me? More, the blacker the line is, that means you have more activity. Do you see more activity in this region?
Yes.
Very good. So that means you have these neurons started to firing crazy when the ball was supposed to go into the left. How about this trial to the 0 degree? Do you see more activity or less activity? Less. So the neurons actually inhibit during this direction. So what you can see here actually is if we plot the activity of the neurons based on the degree of the movement, we're actually generating a tuning curve again. Okay, tuning curve. So we can see that every cell has a preferred direction. So what is the preferred direction for this cell? This cell have the preferred direction at 180 degrees. And some other cells may have a preferred direction to 0 degree or 90 degree to 70. So depends on the cell, they have a different preferred direction. And if you're sampling all these cells within for that particular interested region, for example, if you sampling all the primary cortex, you will find that all directions actually are represented. They have neurons going different direction, prefer different direction, and all the directions are actually represented. And you can also see the tuning curve is actually pretty broad. It's not very narrow. Okay. So if we do the experiment to different regions, for example, motor cortex or supplemental motor areas or parietal lobe, and you can see that they're all showing some kind of tuning. And for example, if you're looking at the motor cortex as we have seen, this is very directional and it's also muscle dependent. So we know this is a homuncular man in the motor cortex, right? So if you putting the electrodes to a region that is supposed to be innervating your facial muscles or innervating your your arm muscles, they are going to be this is muscle dependent. And the supplemental motor areas and the premotor areas, this is a context dependent. So really depends on what kind of sequential movement this is within. Is it going to within? Am I withdrawing my arms and play tennis? And is it a part of a sequential movement? So those cells are mostly sensitive to a particular sequential movement. And the parietal lobe also is showing this kind of directional tuning, but there's more of the location, target location oriented, and they're goal dependent. So why this information is useful? If we recorded for all the cells, and then after combine all the information, every cell is kind of firing, and get a summation out of all of these cells, you can probably predict what the actual movement is actually going. If you recorded all the muscles of your upper arms and in those motor cortex, and see who is the desire, who wants to go firing to the 90 degree, who wants to go to firing the 0 degree, which cell have a bigger voice, which means they're firing more rapidly, and you can probably predict the movement of this arm. So this is we call this study called a vector analysis. Okay. So basically, if you have simplify it a little bit, and then looking at the 2 cells. If we have 2 cells, one cell have a most sensitive direction is at a 180 degrees. And the other cells is at the most sensitive to 90 degrees. So for the first case, if the cell 1, the purple one, is going, because it's going to the left at 180 degree and it has a very strong voice, so firing very rapidly during that trial, versus the cell 2, which wants to go upward, doesn't firing so much. So the some information of the the output, ultimately the output is going towards the left, a little bit shifted upward. Instead, if in another trial, your cell 2 becomes really firing rapidly, and versus cell 1 has a much more silent voice. And this directional movement is, you can predict, is probably going upward, a very little shifted to the left. So basically, if you sum the activity of multiple cells and each cells vote for their preferred direction, and based on the level of activity each cell has, they can cast a stronger vote or very weak vote. And the movement actually is, when you summarize, as we're showing here, is very much matching with the summed voting from all these cells. Does that make sense to you guys? Yes or no? Yes, thank you. Okay, so I really want to show you this amazing movie using exactly what the information we have talked about. Okay, so this is oh, what is happening? Oh, this is really, I have to click multiple times here. So, just give me one second. This is a really amazing movie showing you how and after this we will okay, so this is the arm, the machine arm is completely controlled by the monkey, which is recorded electrodes that popped inside of the monkey's motor areas, and receiving the information about this activity from those motor neurons. And then this monkey is trying to, so the machine basically is translate that information and using the vector analysis and going to pick the food. Okay, so this is actually controlled by the monkey, but if you see the monkey's hand at the bottom, they're restrained, and they're restrained, and you actually so this is, yes, go ahead. I have no idea. Yeah. I won't think it's too long though. You basically need is to have several directions. So this is three-dimensional. So you want to know who is going all these three-dimensional different angles, and how these